So we're going to probably be a bit of a, hopefully each talk is a bit of a palate cleanser for the others, so we can get some different areas of questions going. Ours is not going to hit you with, what is the mathematics behind deep learning and all that stuff that I'm sure you get with all the time. Simply just a couple slides we're going to go through. Maybe a couple use cases we do that'll hopefully pull it into why we're asking the questions we're asking, and that hopefully will motivate a good conversation moving forward.
Sure. And I should probably mention, just to put the plug in, Vertex Labs, we're basically a deep learning, machine learning consulting group. We do a lot in the biotech space, but we're not really only in that space. We tackle a lot of things because of our perspective. So let's just jump into some examples here. Now, one of the things we do work on right now is spectroscopic analysis. And this is, of course, probably not just us. I'm sure many people work on it. And with machine learning tools, we can do a lot more with that. Now, some of the things we can do, for example, are actually measure things at very low doses. So if you're dealing with something such as low dose medication and you're trying to make linear models, well, at some point that's going to break down because noise is inherently not linear. In fact, we find many times noise has very nonlinear, although predictable patterns, but the standard is to use linear models. So we can deal with things at that level, whereas normally, of course, we're only looking at peaks in the spectra.
Yeah, so to bounce off some of the stuff, maybe not necessarily exactly what Michael was talking about, but so a lot of times we'll be talking to some of the best chemists and spectroscopy experts, be it Raman or whatever other type of spectroscopy, and they'll be looking at certain types of peaks and they'll be looking for the active pharmaceutical ingredient, and they see an obvious peak and they go, okay, that's pretty much what I expected. That's one. Maybe they see two and they can go, okay, that kind of makes sense. But after a certain amount of peaks, there are models that are basically based on regression and principal component analysis and things like that, least squares for some of the better ones. They break down after a certain amount of perturbation from artifacts of the process or noise that's just inherent in any type of thing, especially if you guys are passing it through filters like spectroscopy tends to do. And deep learning methods, if applied correctly, tend to not do that. And what they can really do that's, I think, interesting is not just boost your accuracy in detecting that key pharmaceutical ingredient, but rather what you're seeing. So, okay, you're seeing a decent amount of noise here, you're seeing a decent amount of noise. That can tell you what part of your process actually was contributing to some of these peaks, because it'll have a different pattern, it'll reflect. But if you're looking at this through a linear lens, you can't really detect things like that.
Yeah. Probably one of the key statements there is don't just throw away the noise, but analyze it. There's interesting things in all different types of noise, and that reflects both our biases and our models and the state of the science. And to bounce off of that, we actually can do quite a bit of noise removal. Now, this is just an example from the image domain because it's a lot easier to visualize. Humans naturally are pretty good at dealing with nonlinear signals. Traditional math is not very good at that, actually, regression models and such. But noise tends to be very nonlinearly correlated, as we discussed before. It turns out if you can make a model that can learn those nonlinear correlations, we can actually have it try and remove the noise. And I don't want to call it enhance the picture, but really filter it and clean it up. It's not CSI or anything crazy like that. It actually has some very fundamental principles to this. Now, to go even further here, not everything is deep learning and not everything is machine learning and so on, but not every time does it have to be independent. Now over here we have a really simple decision tree diagnosis of diabetes versus not diabetes based off of a few features, which are glucose measurements of different types. But feel free to extend this to more complex problems with many enzymes or disease pathways and so on. Now, let's say I'm going and trying to diagnose something, and I follow this tree because that's what my model said. Now, what's interesting about this is it splits based on powerfulness of each feature of each type of measurement. So right off the bat, we know, without our own bias as to how we think the disease should work, we do know how well does the data tell us what is related to the disease and whatnot, and in what order. But it doesn't just stop there. Now, as we go on, we may see that some data or some types of patients take a lot more data to really actually diagnose, whereas other people can be diagnosed fairly quickly. This leads into actually some ideas about population segmentation. Maybe people with diabetes are not all the same. In fact, maybe we should try and find more patients like this and actually investigate further so we can go deeper into this.
Yeah, as we heard earlier, I mean, ideally, you can develop lenses that are able to look at the individual in medicine, not just how we'd like the individual to be. So with the decision tree, and this is an inverted decision tree from actual deep learning methods, but even with the decision tree itself, it will scale with the complexity, or it will attempt to at least scale the complexity that exists in the phenomena, rather than have preformed pamphlet judgments like maybe a clinical a physician would. Not that that's the best way to describe it, but it is a fair assessment to a lot of what they do. There's a prepackaged element that goes on to a lot of clinical assessment, and even those in many research, especially the ones that we encounter. So while you do lay subject to however the data is, and that is a problem, don't get me wrong, that's a huge problem, you at least get the chance to have a better assessment of where in the data you're missing. Because if a certain part of your branch goes down less, and if you see that you have less data in that area, but you're seeing some saliency for that in some subject, that can tell you where you now need to go collect that data, where you now need to go form new hypotheses. So one of the underutilized areas for deep learning is actually in hypothesis generation, not necessarily in just getting a better metric score for air or whatever you like, or a better confusion matrix for your confounding problems.
Because in the real case, you're not going to take your data, get a 99% diagnostic accuracy, and just run with it. You're probably going to get something like 30%, realize the data's trash, there's a lot more work to be done, and we don't even know what to collect about the data or what types of patients there are. So what we really should be doing is maybe thinking about using these techniques to help us decide, how do we explore? How do we come up with new hypotheses? How do we get a handle around what this disease means, or even if it's a single homogeneous thing, which it probably isn't. So ultimately, what we're really trying to get at here, given all these new tools, and this is the surface, there are many tools both in machine learning, deep learning, and other areas of science. Is it time for a new scientific method? Now, the scientific method is predicated on quite a few ideas, one of which being that you can make an unbiased hypothesis about what your experiment should result in, and as well as the exact opposite of what you learn if your experiment fails. Now, the idea, or should I say even fallacy, that we can make these hypotheses without any data is quite silly. In fact, we're constantly using data to do these. We're just not actually talking about it. We're pretending that it doesn't exist. But our scientific method is not really all that different from our machine learning models or methods. In machine learning, we have some sort of training data, build our model off of that, and then it has some sort of theory or hypothesis about how the process works, and then we evaluate it on the test data, the experiment. As an experimenter, as a scientist, I'm doing the same thing. I've seen a lot in my 10 years or 20 years or whatever in my field. I have some idea of what I think should happen. And now what's interesting about that is that those memories, or that training data, is different from that test data, because you're going to create an experiment off of it. And that data is slightly degraded because it's our memories over time. So it's been pulled from multiple samples, slightly degraded. And from what we know about machine learning, that actually gives a lot of generalization power. So maybe it's time we make some of this more explicit and use both of these to feed back off of each other.
Yeah, so I think, as we know, the scientific method is actually predicated by the statistical method, which actually presumes a lot of the areas that we develop the scientific method in. And I think what Dawer is trying to get at is the idea that the scientific method is a little biased already in its own procedure. And as researchers who don't have necessarily agile environments like software development and things of that nature, we are very subject to whoever is above us in directing our research, or just our own selves. So if we're going to ask questions about what to do next in hypothesis generation or an experiment, we really ought to have something that can entertain way more variables than we're capable of, we're interested in, or are filled out from our previous biases. So I actually think machine learning and techniques like this, because they function similar to the human brain, are really powerful agents in creating a scientific process that can entertain way more possibilities.
The machine learning isn't reasoning deeply about crazy theories about how everything may be linked, but what it can do is entertain a lot more possibilities of hypotheses at that level of deduction that you're working in. And that alone, alongside with our experience and ability to traverse those levels of deduction, gives us far more power that we're just ignoring at the moment. It is time for an update. All right.